நம்ம போன்ல இருந்தே நம்ம என்ன ஜாயின் பண்ணி பார்க்கலாம். போன்ல
Hello, ma'am. Ma'am, can you hear me, ma'am? Maybe we can.
Could I connect my computer? Okay. Just HDMI.
Can you help?
HDMI or? Do I have to be online or is just connect to it? Okay. So
how did you do that?
Can I connect this computer by any chance so that we don't worry about movies, translation?
I'll call that guy.
Oh, you need to. Okay, if it's difficult, I can try and.
No. Suresh, you can also do another thing.
I can just put on Google Drive.
No. You can also log in from there.
Yeah. Oh yeah. Is it on Zoom? Is it Zoom?
Google. WebEx.
WebEx. Okay, I can just share my screen.
Share them, so we can sit here.
Let me see if I can just make sure you sent me the link.
Link is available. You can join that. You will make it as a host.
Okay. Google connect online.
Look at that link.
Can you do ITM Wi-Fi? Yeah. You can log in. That's it. I don't have that phone.
Okay,
he's getting me on Wi-Fi. Then I should be good.
Then இது HDMI இல்லையா எங்க எக்ஸ்ட்ரா HDMI
இருக்கு சார் அந்த கனெக்டர் நான் ஆபீஸ்ல
Suresh, come here. There should be all the utility available. Anything here. So I think we should try that.
That is much easier. Screen mirroring. Okay. Okay, connected. Good.
Hello. Good morning, madam. Cold is not improved a bit. So I went yesterday to doctor. Actually, I thought of calling you yesterday evening. So then they said following day and. Okay.
Oh, yeah, yeah, yes. It won't come there.
Yes. So I need to take, I thought of taking some over 650, but then they said no. Yeah, that's the. Yeah. There was a right time I thought of it. Tell me, madam. So I'm working on that one. So I have already blocked it because corporate the rooms are too occupied. Now I have a department seminar room was available. I already blocked. In class something today I will reach it. Well, Suresh is you might be knowing. Suresh Dhaniyala is a professor in Clarkson University. He also worked. I just share as I share that meeting link to. Today you're giving a talk. So maybe in the afternoon I'll be meeting. Then after that I'll also do that. How many students will come? How many students will come? 50 is okay. 50 is okay. 50 should be fine.
In the middle of this. Oh, no, capital.
There is plan for some, what time is the plan for
Yes, this. Don't see the dot.
Yeah, so we will have to meet some this plan.
It's not even consistent.
Sure. We'll clarify. Sure, but today evening we'll plan some. Thank you. But it's not working. Suresh, you can also use.
No, I think it's coming. You just load it. I think it's working, but yeah.
I just see
yeah,
that
it's coming. It's coming.
Connected sharing the.
It's coming. It just needed to be done. Guys, from the browser?
Okay, it's fine. Hello. Just join the meeting. Just.
Oh no, put my name.
I make him as a host so that
co-host and whatever. Okay, check. Suresh, you are okay. The share. Can you mute your mic?
Maybe if you plan to come in, maybe another we can discuss that.
Just checking it. One.
Is it okay?
Oh, share task.
Okay, I'm muted finally.
Just one of you just check whether he speaks. Is it properly capturing?
And then also check and see if it's correct.
One of you just join online and. Okay, so Suresh, you can just say.
Is it okay? That's good. You can hear me and the screen is okay? You can see the same screen?
Yes, yes. Okay, good. Now we don't actually. Okay. Yeah. Okay, Suresh, now you can have some interaction with before we start the. Maybe each of you just introduce. Lakshmi has already done. Maybe Ashwin, you didn't take find time. Chaitra has already mentioned about everything. Ashwin also looking, but
Everybody here works in your group. Okay.
I'm also looking.
It's a big group. Okay.
So hello, sir. My name is Ashwin. So and now I'm working as a postdoc with Professor Shiva.
Okay.
So my PhD mostly dealt with urban air quality management, and like we were trying to fix few issues. One was like the lack of monitoring sensors. So it's captured from CCTV cameras to 8.5 levels from that and tracked by pollution levels. So I used ResNet-based CNN
Good morning.
to classify that, so that the was to link with the traffic junctions, and then we can get a high resolution data for PM2.5.
Yeah.
And then the second objective was to fuse data from different monitoring sources, like fixed stations that we have in the regulatory system. Then the mobile monitoring that we conducted a 2-week campaign covering the entire Chennai. So we want to integrate fixed sensors, mobile sensors, satellite data, as well as dispersion models. So we use data efficient models, basically enough for us fixed models to fuse all this data from different sources to create a map for Chennai. So that was my second objective. And third was like to look at how people perceive air quality, so that we can nudge them to take better decisions, and as well as to look at the relationship between the different factors and how people perceive air quality. So I conducted qualitative and quantitative surveys. Like it was like 19 people. Took them to the terrace, showed them the scenery, and asked them to rate the scenery based on air quality and visibility. And then we tried to correlate it with their demographic characteristics and their knowledge. And based on that, we are also doing thematic analysis, qualitatively how they perceive air quality. Then we also did a 900 participant online survey to understand their, to cover a larger group, to translate the 19 surveys with the 900 surveys to understand how they perceive and how we can integrate perception to air quality management frameworks, so that we can start from monitoring, management, and also the follow-up with perception and participation.
It's pretty interesting. There's a lot of overlap. We've done some work on photograph-based analysis. We ended up not using machine learning because the machine learning will not go from one site to another site because the background changes and so on. I don't know if so you have a very location-based model. And we used analysis of Twitter data when Twitter was on Twitter to do sentiment.
You can always talk to that one.
But there's some overlap. Thank you.
Mine is on microplastics in indoor environments. In my research, I'll be concentrating on characterization of airborne that was indoor environments, followed by source apportionment modeling to understand the major source of, and finally ending up with the health impact assessment and mitigation based on practical experiments. That is my research. As of now, I have completed my objective one, working on the identification.
How do you recruit or in the indoor spaces? Do you go to people you know, or you have to?
We'll choose the people like the spaces.
Okay.
Yeah.
You actually need some part of
campus also we have many residential houses. It's easy for me to
So, but how do you ensure that you get different kinds of houses, and like if you go to campus houses, they may be similar.
Like how I choose means like I choose 2 indoor residential.
But I just explore
because those houses were very close to the traffic.
Okay.
So maybe the exposure may be different and source will be different. And also in the active sampling we concentrated mostly on industries. But inside campus we have a very nearly 50 because we plastic. Asbestos and incineration plant we have inside the campus. Those kind of industries.
we would like to invite you to.
that's should be interesting. Thank you.
My first objective, what I did was I entering in major vulnerable locations.
I will just explore the overall there's national information, the Aerospace, also.
Is the auto rickshaw monitoring is everything was a result we also doing something like it, right? Okay.
We can get
The last 2 years,
Okay.
we had different approaches to these token structures. We were using
I see.
So monitoring in different urban work environments to understand the exposure of different people working in the urban settings. These studies are done in industrial settings. And I have calculated the health of people in urban areas based on road traffic movements. And based on the monitoring results as well as traffic data, I have done modeling and produced maps for certain locations. And finally, I have come out with a framework for management of urban.
Okay, it should be interesting to see how. No, I will.
check my environment. You just draft in and also the template, the way they wanted the response. 2 things if you send it to
Basically, I'm working in air water interaction of microplastics. So, literature, so
Just started. Okay.
pretty much completed my course. Okay.
Good luck.
Project engineer at the projects team one is national clean air paper. They are very official interaction. I also know social.
So you can forward the email communication saying that we are submitting a proposal. We invite you to put the so please send your response in
It's mostly just modeling or measurements also.
Yeah, measurements.
Here in Chennai.
Other parts of India, like Northeast India, North India, North India.
Hello, sir. I'm Shobhit. Finally, so I have done my monitoring in Namely. It's a thermal and mining area, and from there I've collected PM samples and I've done chemical analysis.
So mainly it's coal.
It's lignite.
Lignite, right.
So then I've done chemical characterization, trace metal ions, and then
How far from the site? Are you mostly close to the mining site or far away?
it's like spread out in 10 locations.
10 locations.
In and around me.
Okay. What is the objective?
Like source apportionment,
Okay.
and then
Okay. And is it who's funding the project?
it's like sponsored from Naval Institute.
Okay. Usually, people who are mining don't want to know what they are doing to the neighboring neighborhoods. I'm surprised the mining folks want to know what they are doing. That's good though.
Sure. That's interesting. So during this project, they were had to get expansion from. They have only one power plant. They wanted to go for a second power plant.
I see. Okay.
They wanted to have some reliable agencies to validate their data.
Okay.
That's why they came to us.
Okay.
So at times the head of the department were also having another project than I did.
Okay.
They wanted to have this project and they had it.
Are you responsible just for monitoring or it's also the mitigation?
It's a complete year. In fact, we experimented first time electric vehicle based mobile monitoring system for them.
Oh, okay. Yeah. Yeah. Right, thank you.
Hello. sir. So I am involved in regular emission testing, sir. So we are taking measurements in real world condition of different vehicles, especially heavy duty vehicles, and then developing some machine learning model. Also, different exposure that pollutants and drivers faced in different activities of these heavy duty vehicles, different settings like in construction techniques and waste, port areas, the transportation of cargo logistics costs, terminals. Thereby, we are simulating the emissions and developing some machine learning.
Okay. So this is, sorry, the heavy duty, I didn't catch all of it, but the heavy duty vehicles on urban roads or more in, like say construction sites or
Yes, sir. We have taken some off-road emission measurements.
so there's two kinds of emissions here, right? Then there's the combustion tailpipe emissions, but then there's also all the resuspension of unpaved roads and so on.
Yes.
How do you separate it out?
So we have potable emission gas and light. We directly connect it
I
to the
see.
tailpipe.
Okay.
It measures the tailpipe.
Right. You're measuring directly from the tailpipe. Okay. Good. Thanks.
I'm Chandrasekhar C. I completed my PhD from IIT Hyderabad. So recently I joined as a postdoctoral. My PhD topic was on modeling vehicular emissions in real world driving conditions.
Okay. And your postdoc work is some similar
Related to air quality.
You just started.
My area is indoor air quality monitoring and health research in the rural area in Kerala and Karnataka. Actually, I am doing my monitoring and after that I try to analyze the samples and do the categorization survey. Then based on that, find out the source of punishment. Then along with that, I am going to help.
Rural meaning more, you're looking at indoor would be a lot of cooking emissions and so on. Okay. Because we did a lot of cooking work also with Kalpana here. And so some of our interest in sensors came about because we were carrying big instruments into rural homes, and there was just a lot of work to connect and so on. So it's still very useful work. Yeah. Thank you.
Yeah, running out of time. Maybe we can continue with
Okay.
that. We have a startup group.
Okay.
So I'm just mentoring that.
Is
That's what these devices will.
Okay. Yeah. Happy to take a look at it maybe after the talk. Yeah.
So we can start. Okay. So we can do it here only. Connected.
Should I come there?
No, right, sir. I think. But yes, you have to move that slides and other things. Okay, so just 1 minute, Suresh. Just a few minutes, you can disconnect your slides.
Just so
Only for a minute.
you can just stop share.
Stop sharing, yes.
That is lead meeting.
The SDMI, you just remove the SDMI.
Oh, okay.
It will automatically. It will have to pick up the other one, yeah. Okay. Hello. Maybe we can just. It's okay. Still, it's is. University. You can also use. I have to unmute you. So maybe this mic.
So actually, we can mute all, and then only no, mute all. Now you can.
Hello. Hello. Still it's pretty.
You unmute that.
Hello.
Now it is done.
Hello. Can you hear me now?
Yes.
Okay. Good. Very good, right? Yeah, very good morning to all of you, and welcome to Air Quality Management lecture series. This is the 56th month lecture. And thanks to Professor Suresh doing today's talk. So we started this Air Quality Management lecture series in October 2020. It's more than 4 years old. Basically, the idea of this lecture series is to bring, the young researchers, scientists, engineers, and practitioners to share the latest advancement in theories and applications related to air quality management. So this lecture also covers recent developments and innovative ideas and technologies to address air quality. So these are all our past speakers, and we started with the first lecture with Dr. B. Sengupta, Member Secretary of Central Pollution Control Board. And as you can see that we could able to get speakers across the globe. They're all, the last lecture was given by Hekta Sharma, the lecturer, researcher at University of Southern Queensland. Just to give, in order to initiate more and more activities in the area of air quality management, so we also started an air quality management association, and where everybody is welcome to join this association. It's a small group, and we try to see that what best we can do in order to improve the air quality in the at the community level. So again, it also provides more of interaction space for both students as well as the professionals. So this is another major project which helped us clean environment for planetary health in Asia. It's supported by UKRE, and we started a network, and that was with this project we could able to start this air quality management lecture series. And one of the idea of this network is to look what solution will be work for a particular environment, and can we translate that to another areas or environment, and we can try to learn from examples of one place to the other place, and see that the socio-economic benefits can be addressed. Of course, we started this Indian International Conference on Air Quality Management. It's a 10th year now, so we continue to work in this area, and we would like to see that more and more participation attending this national conference, and to bring all of them working in the area of air quality management as a one platform. And this 10th year we were going to do, we are just discussing it. We thought initially do this particular conference in Abu Dhabi, but there are some challenges coming out. So we will try to announce it maybe within next 2 weeks where is the location. So now today's talk will be given by Suresh Dhaniyala. I request Ashwin to introduce Professor Suresh. Thank you very much.
Professor Suresh Dhaniyala is the Bayard D. Clarkson Distinguished Professor in Mechanical and Aeronautical Engineering and the co-director of Center for Air and Aquatic Resources Engineering and Science in Clarkson University. Professor Dhaniyala's research interest lies in indoor air modeling, design and development of novel air quality and bioaerosol sensors, AI and ML based ventilation systems, and sensor integration with building management systems. He has been part of many committees, including the Aerosol Science and Technology, and committee member for safety of Mars sample return, and NASA committee chair on evaluation of Mars 2020 contamination control and procedures. And he's also the current vice president of American Association for Aerosol Research. So he has varied interests, and we welcome him to give his talk today on the topic building ventilation optimization driven by network air quality sensors. We welcome you.
Thank you. Thank you very much.
Maybe you can share that one.
Sure. Should I just present one here?
Should we record that?
He can share it. Recording down.
All right. Okay. Thank you for the introduction. Appreciate it. No, I'm just here, so I should be fine. Can you see my mouse if I move it?
Yes, yes.
Okay. Okay. So I'm good. Appreciate the introduction and the invitation to present here. This what is talking across the room here. Clearly, you guys are doing a lot of work in related fields. I'm actually excited to see that. And I think some of the stuff that you guys are doing is very, I would say, next generation with respect to what's important with microplastics, with indoor air, and the techniques you're using to do outdoor air. I think there's a lot of overlap, but I also see that a lot of stuff you're doing is excellent, very cutting edge. So, I'm happy to present it as I'm going through this. If you have questions, feel free to stop. Of course, at the end, we have time for questions. Again, so a lot of what I'm going to present will have a bit of a US context, but I don't think it's entirely disconnected from what is here. But there are some, things that are probably different here. But in the US, I would say that the one thing to note is that the buildings are a major consumer of energy. I would say I think some of the statistics there are 40% of all the energy being used is used up in buildings, and 40% of that, or 30% of that, is used for ventilation systems. So, and this is, I think, a sort of a big difference, I would say, from many of the buildings here versus in the US, because many of the places there can be pretty cold and pretty hot. So there is summers can be hot, winters can be cold. So the air has to be continuously, the temperatures have to be maintained. So you can think about here, what you have is an air conditioning system that keeps the place cold. That's all you need, in summer. In winter, you can turn it off or you can reduce it. But when you have to put a whole heating system to it, you can either have an integrated air conditioning, heat pump kind of systems, or you have to have two different systems. Usually what there is a central building system that provides hot air or cold liquids to provide air conditioning of both the heating and the cooling side. And because the temperatures can be pretty hot and pretty cold, the energy used up for just the ventilation control is significant. About 15% of the total energy is just in the ventilation system. So you can imagine if you're trying to reduce energy use overall, and you want to reduce greenhouse gas emissions, you want to be more sustainable, tackling ventilation systems becomes very important. So this is, in the buildings, it says about 35% is used up for ventilation and air conditioning. We do a lot of work in lighting, right? I mean, you see a lot of people, you move your bulbs to LED, and then there is motion sensitive lights. So you leave the room, lights turn off. But all of the lighting is only 11%. The ventilation system takes up 3 times more energy. We have not done as much to save that energy. Just if you think about ventilation system, so for a long time in the US at least, the emphasis has been to build very tight spaces so that you get no energy loss. When it's very cold outside or very hot, the last thing you want to do is heat up the room some more or cool it by losing energy. So the emphasis has been on very, very tight. So if you come to my office in Clarkson, I cannot open my window. It's airtight. But you know, but if you think about ASHRAE, which is the American Society for Heating, Refrigeration, Air Conditioning, and there's Indian versions of that, and they recommend what your indoor air quality should be, and they recommend that you need a minimum of 10% of the outdoor air should be brought in, and probably more. Why? Because as we sit here and we're all breathing out carbon dioxide, which can, when the concentrations go high, can make us feel drowsy and so on. But other thing is concentration. We're also have breathing and talking and putting out particles, and then that there's possibility of infection. All of which we can reduce by bringing outdoor air. So DOE say keep it tight, don't interact with the outside, but the ASHRAE requires us to bring in outdoor air. And then during COVID with CDC, it was then, it was always known, but then became very important that the ventilation system is one of the top three means of controlling infection. So everything as we're putting out, as I'm talking and breathing, putting out particles, can be, the ventilation system has to make sure that these particles are removed quickly, right? So the ventilation system has different pushes and pulls, and what we have right now, it's sort of a function of all of that. But just to sort of picture the whole thing here, our indoor spaces typically will have people emitting particles out, and as we all walked into this room, depending on how much they mopped and cleaned this room, there would have been some particles to begin with, and as we walk in, we resuspended. Some of those particles are biological. As I'm talking, big particles can settle. As I walk later, these particles can resuspend and you can breathe it back. So resuspension is a big source of particles. But then there's also losses, by diffusion and deposition and other effects of diffusion, we can lose particles everywhere. And then this air, like I said, in these tight buildings, you don't have oftentimes you don't have a window to open, even in this space, you probably don't open windows here. So the air is usually, there's a vent out, we'll call it return air, and then there's a supply air. I don't quite know if this space has, but your office in NIC, I think it's got an out and an in, and in between out and an in, it can go through, some conditioning. It could be, so the conditioning could be a filter, for example, or during COVID, people are putting in a lot of UV irradiation to kill bacteria, and so all of that can happen, and then you push it back. But you want to make sure that you bring outdoor air. Like I said, the guidelines is to bring about 10% of the air you put in should be outdoor air. So I'll talk about one of our classrooms, we're bringing in a lot of air. We'll talk about some numbers, but in general, about 10% minimum. More is better. And then you have to, of course, throw out the equivalent amount, otherwise you're going to be just pressurizing the room. Right? So again, there's all sorts of guidelines from ASHRAE on what to do for energy efficiency, air quality and health. But in general, what we have usually considered is that if you want good air quality, it is coming at the cost of energy. So meaning, if you want to bring more outdoor air here, and today is not a very warm day, but still probably will be 90s in the afternoon, and I think it's probably maintained in 70s here. So that 20 degrees of heat needs to be removed. So if you're continuously bringing outside air, your energy is going to be much higher. Same thing in your car, right? You sometimes have a recirculation mode or a fresh air mode. Recirculation will be less energy because it's already cold air. So during COVID, one of the questions was that we start putting in all of that UV irradiation or bring more outside air, can our systems handle it? So, because again, all of these are assumed to be more energy costing, and often it does. So our question is, can we optimize the ventilation system? Which means, we want to minimize the pollutant buildup. We want to minimize the, ideally, we want to make sure there's no pockets of high pollutant also. So we want to minimize pollutants not just on an average, but everywhere. We also want to make sure that while we do this, everybody is nice and comfortable thermally. That's why here you got 4 air conditioning outlets. Otherwise, I'll be nice and cold, but you may not get air there, right? So we want to usually minimize that. And in all of this, could we be minimizing energy? That's a big question mark. While we also want to maximize the rate at which we remove pollutants. So, there's no escaping. As we're talking, we're going to be putting out particles, and if they're infectious, particles are problematic. But if we can remove it as quickly as possible, we minimize infection rate. So, there's all sorts of constraints. Like I said, we want the temperatures to be in a narrow range. We don't want too cold, too hot. Relative humidity should be in the correct range and all that. Okay, so so then the question is, how are we doing it right now? Okay, and if I have had to guess, because I think about 70 to 80% of buildings worldwide, we are only monitoring temperature. Well, we may be monitoring temperature and relative humidity, maybe 2 parameters, but we are only controlling probability temperature. Globally, it's not just in India or US or in most places, except in at least in the US, in hospitals, you are required to maintain humidity. And some of the some spaces they do. Probably, in malls they might, because there's a lot of incentive to keep people comfortable and shopping. But in many office spaces and so on, you keep the temperature in the right range, but humidity is not perfectly controlled. But we definitely don't control carbon dioxide and VOCs, other pollutants of particulate matter. So, our question is, could we integrate sensors with building automation systems? So, if you go to most hospitals, definitely in the US, probably in India too, they're all of the monitoring of temperature, relative humidity, and anything else that's required by law, all of that goes to a central computer that then drives the system. So these building automation systems are built by Siemens and Honeywell and Johnson Controls and so on. And they use a protocol called BACnet, Building Automation Controls Network, or Modbus, so very common protocols. And so the key is, how do we drive these systems? And I would say that a lot of systems right now are being driven by what we call rules-based algorithms, which means you say, if the time is 8 a.m., turn on air conditioning. If it's 6 p.m., shut it down, right? That's a rules-based system. What we think is that, of course, I'm going to say that if you're going to optimize it, I'm going to argue that that is inefficient to do that. For example, as soon as we are done with the conference here, we are all going to leave, and we might turn everything off, or we might forget to do that. So the rules-based stuff, or driven by manual operation, is subject to some inefficiency. We'll see how that works out. Okay, so how could we advance sustainability here? First is for us to just monitor and see how well are we doing currently. We cannot improve if we don't understand what we're doing currently, how we are doing currently. So what we have done here is first in trying to monitor, we try to say what's available for tools. What we understand is that we want to monitor the air quality, temperature, and all that. So it turns out, do I have a picture? Yeah. So there's a lot of low-cost sensors available for carbon dioxide, temperature, relative humidity, very inexpensive ones. Volatile organic compounds, now you can get metal oxide sensors, again, pretty inexpensive, very small. And then these are, you can get commercial low-cost particle sensors that are about this big that can give you a few metrics of particles, like PM2.5, concentration particles, smaller than mass concentration particles, smaller than 2.5 micron. You can package them all in a box, and now you can start monitoring it. But how good are these measurements? So we need some research-grade instruments to compare. So we put all of those to monitor, and then of course these ones we can put tens of these in a single room, in all sorts of locations around the room. I'll show you what we have done. But the research-grade ones, we'll have one set, and we'll put it judiciously. Okay. Okay, I'll just take 1 second in explaining how these the low-cost particle sensors work, because it'll become important when you see that they give you very different readings, the research grade particle, number one. Number two, if you're interested, I'll talk a lot more about it at 3:30 in the chemical engineering department. It's all about sensors. We'll talk about it then. Okay, so in these low-cost sensors like the one that I showed here, the green one, Syrian SPS30, these all have a laser diode. Unlike the standard lasers, gas lasers and so on, these laser diodes are with semiconductor based ones. And so these ones are very small, low powered. And then these ones you can get different wavelengths, and they're usually a pretty narrow wavelengths. The other lasers can be broad wavelengths. These ones are pretty narrow. Then there's a focusing lens. You usually focus into a very, very tight beam that gives you very high intensity, but in a very small region. But then the other regions with lower intensities and bigger beam width, it's a bit of a complicated laser path. When the particles interact with it, they scatter light, and that scattered light is collected by a photodiode, and that photodiode signals are then interpreted to get concentration. And the interpretation is somewhat complex, and I'll talk about that at 3:30. It creates results that require a little bit of work to interpret. This is what it looks like. Again, like I said, they're about 1.5 inches by inch or so, or 1.5 inches by 1.5 inches or so. So take about 30 centimeters by 30 centimeters. And then how do we? So we evaluate the performance of these sensors by putting them in a chamber. We can inject particles, different sizes, different compositions, to try and see how well they do. And just a very quick glance of how well did they do. So we put in ammonium sulfate, dust, and smoke generated by burning velcro. And so these sensors, so these are two of these, plant tower and SPS. So we compare it against a research grade APS instrument. What we see is that there's some composition dependence. So different colors are different compositions. So some composition dependence. So if there's no dependence, a one-to-one line will be right there. There's some small dependence because it's not exactly the one-to-one line, but it's not too bad. All right, it's not too bad. That's the picture here. If you come to the talk at 3:30, I'll say it's pretty bad because I use a different data set. This one is polydispersed. There we started testing more monodispersed. Depending upon size, it will be very different. But for a lot of what we're trying to do here, it's not too bad. All right. Okay. So now the question is, what does indoor air look like for air quality, for thermal comfort, and for energy? And then, before we optimize, we want to understand that. So, so what we did is, so we picked a classroom that I actually used to teach at one time. So it was very obvious. I said, let's start monitoring there. This is a pretty reasonably big classroom, houses about 120 students. And the nice thing about picking this classroom is sometimes there will be 100 students plus. Sometimes there'll be only 20 or 30 students. So there's a very wide variability. Sometimes it's used, sometimes it's not used. So there's very dynamic usage. And the other most interesting thing is oftentimes in our campuses, you might have 10 classrooms, or 10 rooms, and they'll all be supplied by the same air handling. Some blowers and push air, and then gets divided in the 10 rooms. But in this case, this particular classroom has its own air handling. So if you make a change to this classroom, it doesn't affect anybody else. So we can make some changes and not impact anybody. So a lot of reasons to pick that. And box models, you probably all, I guess, have done simple box model. That's all. We started off by first understanding what would we expect from the classroom. Well, in any room, if this is a box, if you consider this as a box, you got a source that could be all of us putting particles, for example, or carbon dioxide. You could all be emitting carbon dioxide right now. We should be. And this carbon dioxide you won't lose, but if it's particles, you might deposit everywhere. So you got some loss, but you got flow that's coming in. That's coming in with some concentration of carbon dioxide, some particle concentration. It's going out with some concentration of carbon dioxide and particles, and flow rates. It's coming in with the flow rate, it's going out with the flow rate. It's often equal, but not always equal. Sometimes you might have some leak, right? So you might want to keep, or you might want to keep the room slightly in negative pressure. If you go to a hospital, some rooms will be negative pressure, some are positive pressure, depending on what you're trying to use the space for. So if you want to just model what's happening to the pollutant, you just do a simple box model for starters, right? Yeah. And so you figure out how many particles are injected, or what is the flux of particles into the room per unit time, and what is the removal rate of these particles, and that creates a flux balance, right? So what's coming in, if you're putting in 10 particles per second, you're removing in 8 particles per second. There's 2 particles per second injection into this room that is probably going to build up over time. Or if you're, and so as a function of time, it's very simple ODE to solve, right? You can just do it by hand. You can solve that. The important thing here is you end up with these terms that we will explore in a second here. So you have the initial concentration that then changes with time. It either goes down or goes up depending upon the sign of alpha. And n infinity. So yeah, maybe I'll just show that with the plot. Okay, so so in here, let me put this on. Okay, so in here, what I have is I'm plotting as a function of time what happens to particles where initially I turn on the source. So when we started here, we all started walking in at 11 o'clock. We started putting particles out, and or carbon dioxide out. There would be a buildup of carbon dioxide, right? And so as a function of time, as more and as I'm just, even if just one person here, it's more and more carbon dioxide. If we do not remove it at all, right, it'll just keep building up and up and up and up. But if we are bringing in more and more fresh air, we don't build up as much. The buildup reduces. And where you level off will of course depend upon how much you're putting in for particles. What is the source? How much carbon dioxide am I emitting, or how many particles I'm putting out, and divided by the flow rate at which I'm removing this carbon dioxide and bringing in fresh air, which has less carbon dioxide. And the rate at which I reach the equilibrium depends upon the air exchange rate, right? So that's the air exchange rate is the most important factor here. The air exchange rate is an air exchange rate of 1 means I remove the entire air in this room one time. So if this volume is whatever, let's say 1,000 cubic foot. If I'm removing 1,000 cubic foot per hour, my air exchange is 1. If I do it 3 times 3,000 cubic foot, then my air exchange is 3. So it's just a non-dimensional way to look at it. And mostly indoor air, we deal with air changes per hour. Okay. As soon as I turn the source off, when we leave, how quickly will the carbon dioxide leave? It depends on how much fresh air we bring in. If we absolutely bring no fresh air, right, and we just shove, it's going to remain constant. The more and more you bring, you will go faster and faster. But even if you bring a little bit or a lot, you will eventually taper off to whatever whatever's coming in with the in air. Carbon dioxide is usually about 400 ppm outside. So if you leave and if nobody was here for the next 5 hours, so it'll come down to 400 ppm. How quickly depends on how much fresh air we bring in. Okay. So with that, so we know how to model. Right? Everybody, we've done for maybe 50 years, so we know how to do this. What it depends on is air changes per hour, which usually you can go to the facilities department and say, what is the flow rate coming in? You know that. It is the emission and the source, pollution rate. How much are we putting out for carbon dioxide and particles? That information is a little bit, not as well known, especially for particles. And then what is the loss rate? How quickly do particles get lost? We know a little bit of it, but we don't know that in an active environment. If you have a simple box and you got laminar flow, it's very easy to model it. But in a room with people moving around and creating a turbulent flow, recirculatory flow, what happens is a little less known. So ideally, we like some experimental data in the real world environment, make sure we understand all that. That's where our classroom comes in. Classroom has a door, we can walk in, there's lots of seats in here. The faculty member teaches here. And then what we have here is airflow that comes in through the red, these red in lines. It goes out through the blue lines. And so it goes out through the blue lines through these ducts that are on the top. There's two. There's one in the front, one in the back. So these mix, they come in, and then we throw out, some of that is exhausted out, and then replaced with outdoor air. Everything is mixed and filtered, and then heated or cooled, and then supplied back. Right? Just recirculated back. So that's the whole ventilation system. So in here, we have put low-cost sensors everywhere. 4 in the room, one before and after the filter, the return air, outdoor air, and so on, supply air everywhere. And so these low-cost sensors are, in the classroom, they're stuck in the outdoor, in the line that's going out, removing air. It's in there. And the ventilation ducts above the ceiling tiles, where air is brought in or removed, we're monitoring there also. And then also outside. We want to know what's the outside air quality, so we have that too. So put all that, and then these research grade instruments, we put it, we're sampling from inside the room, and then in these boxes just outside. It can be loud, so we leave it outside the classroom, but the air is sampled out from that. And then we monitor energy and everything. So this energy is monitored to figure out how much energy is used by there are 2 fans. One fan pushes the air into the room, other fan pulls air out of the room. If they're exactly equal, there is no outdoor air. So depending upon how I control these and control the damper, all of this air is controlled by just these 2 fans. And then, so we monitor the energy of the fans, and then we monitor the energy of the heating and the cooling system. There is a heat pump which keeps the air hot or cold. Okay. So we've been monitoring for over 2 years, and so during these 2 years, a lot has happened. We in the US had a mask mandate until April of 2022. The mask mandate came off. We had a MERV 8 filter in the ventilation system. I don't know if you are familiar with MERV 8. It's minimum efficiency rated value or whatever, MERV 8. So that will mostly only remove big particles above a micron, maybe only about 15-20%. If you keep sending the air several times, it will eventually remove those particles, but very low pressure, minimum required. We moved up to MERV 13 in April. MERV 13 is a higher grade filter, cleans the air some more, but it's more expensive to push air through a higher efficiency filter. So that happened, and then we had wildfires in Canada, just 500 miles north of us, and with the winds, we got a lot of particles where finally the visibility in our very, very clean area, visibility was only for, maybe 100 meters because of the pollution level so high. Air quality index was about 400. In Chennai is right now maybe 40, 60, but it's really bad. So we did all of that, and then we had low-cost sensors right through, high-cost sensors only for about a year and a half, and power meters there and so on. So this table tells us a lot has been happening. But here's the story, all right? For 1 week, a typical week, this is what happens on a Monday. Students come in at 8 a.m. This is carbon dioxide concentration shoots up. As we are breathing in, so carbon dioxide goes up. And then as the classroom goes in and out, as the number of students change in the classroom, you can see carbon dioxide changes up and down. All right. And then Monday, Wednesday, Friday have similar pattern. A lot of classes are Monday, Wednesday, Friday, or Tuesday, Thursday. So Tuesday, Thursday have somewhat similar patterns. But there's a lot of stuff happening. We don't know how they're changing the ventilation systems. A lot of things behind it. But just a quick look. And just for reference, ASHRAE recommends that these carbon dioxide levels should be less than 1,000 ppm. There are other standards that recommend carbon dioxide should be less than 800 ppm. And when you have more carbon dioxide levels are more, you also tend to feel drowsy and so on. So if you're driving in a car, carbon dioxide levels can go up a lot. Lowering the windows can help. In an airplane, carbon dioxide levels again can be very high, 2000 or something. But here, classroom is not too bad. Mostly, below 1000, but sometimes above it. Oh, and then just to note, when there's nobody in the classroom, it goes to 400 ppm or so, which is the outdoor value, and goes down there because you're constantly bringing outdoor air and it's going down. Okay, so here's on any particular day, this is what happens. Here's the outdoor CO2 in green, and here's the indoor CO2. It goes up in the first lecture is there. You got 57 students, and then when there's more students, again, there's a lot more increase in there. And then when the students go down, it slowly goes down, and then there's a break for lunch, it goes down. And now you got, instead of 51 students, you got 52, but still goes up a lot more. That is because, firstly, maybe the 51 and 52 students are based upon enrollment. How many students enroll, and maybe students didn't attend. Not everybody was attending class number 1. The other thing is the amount of outdoor air that's brought in could be very different. This might have been, I don't know which they might have brought in a little bit more outdoor air at this time than this time. When you bring less outdoor air, the concentrations can build up a lot more. And then when everybody is done, it decays down, right? So this is what you expect. So the question is, how well does this perform? Now, how do these measurements compare to theory? So we understand I should have put in here. We understand the air exchange rate. So we talked to the facilities department about 3600 CFM. We know the outdoor CO2 values. Students, we assume that everybody enrolled is in the class. Never happens back home, right? But let's assume that. We assume students are putting out 40,000 ppm when they're breathing out with 6 liters per minute of air that we breathe in and breathe out. Again, these are all assumptions. All of these have a range. We need to start putting error bars. We have not done that yet. But here's what we predict would be the CO2 values based upon class sizes and ventilation systems operating, how much outdoor air they're putting in. And that's the yellow line. Sorry, the theory is the black line. The theory is the black line. My bad. The yellow line is what we actually measured in the in one of the locations of the classroom. Red is at the back of the classroom, and then there's another blue line that actually I think is in the ventilation system that matches the this is yellowish color or orange. So think about think about 2 measurements in the room. One is in the orange at the front of the classroom, and red, which is in the back of the classroom. So the first thing is front and back are not the same. All right. So in the big classroom, we have spatial non-uniformity. But in theory, what I talked about in theory was a well-mixed room. That's what we call a well-mixed room. The well-mixed room, you only get one. You assume everywhere is constant, and that's what we get for here. And I think we are predicting reasonably what's happening in at least near the front of the room, which is where the front of the vent is where 75% of the air goes through. The back is about 25%. So most of the room is sort of behaving like theory, but not perfectly. I wouldn't say it's a perfect match. We predict much faster decay than what happens and so on. So, but if I make a small tweak, where the only thing I tweak is the number of students. If I just say maybe not all of the students attended, only some students attended, I can get a match the theory to the theory is black to the average concentration in the room from measurements, almost perfectly. We can almost perfectly predict, right? But it is a free variable, and we don't know that we got it right. And unfortunately, we don't have the metrics of exactly how many students we are attending. So that's new information we're beginning to collect right now. It's a little bit difficult to collect some student-related information because of privacy and so on. So we're trying to make sure we collect just the bare minimum information. But here's one of the days, and here's another day. Even with all the tweaking, we don't get all of the data, but it's not too bad. We can begin to predict. But what we don't predict is all that variability. Okay. So anyways, we've got a theory that predicts reasonably well what might happen on an average in the class, but not necessarily what's happening with all the details. Here's particles. This is very important information here for students who are doing indoor work. These are low-cost sensors. Low-cost sensors don't give you sizing. They give you just a concentration of all particles, beyond some size. So they tell you how many particles there are beyond 0.3 micron, for example. Here is a high-cost instrument where also we can get the same kind of information. Total number of particles larger than 0.5 micron, but you can also get in size range. So what you see is, just visually they look somewhat similar. So total particle numbers look somewhat similar, but what you see is that if you look at particles greater than 1 micron, this is greater than, it should be greater than 1 micron. What you see is that you see a lot of pattern within 1 day that you don't see in the low-cost sensor, right? So when the classes start and stop, particles go up and down. You don't see that. For example, here you don't see that. Here you see a pattern, but that's also noise in the sensor. You don't see this kind of regular pattern that's timed with. That is because a lot of the stuff that we resuspend is big particles. Particles larger than about 700 nanometers or so. More importantly, our outdoor particles are Outdoor particles are largely 300 nanometers to 700 nanometers. There's a lot of particles in 300 nanometer size range. So when you're bringing in outdoor air, you're not just reducing carbon dioxide by bringing low carbon dioxide outside air, but you're also bringing a lot of particles from outside. And those particles are all 0.3 microns, 0.5 microns, and so on. So the outside air dominates the indoor air. Outdoor air particle concentrations dominate indoor air. So if we're monitoring the particle concentrations in this room during the lecture here, you will see that by varying, and that variation will be largely dependent on what's happening maybe with outdoor air, not because of what I'm talking. But when I'm talking, I'm putting out these particles, but there are very few. The concentration is small, so it doesn't, if you're not measuring by size, you miss it. So it is a problem. The low-cost sensors are not good enough to selectively monitor indoor emissions. That's the bottom line. All right. We'd love to say we should use low-cost sensors for it. Low-cost sensors will give you a good picture of what particles are there in this room, but it doesn't separate out outdoor air from indoor generated particles. And remember, indoor generated particles are what might create COVID infection here, or if I have flu, I'm going to give you flu because of indoor generated particles. If I now mix it with outdoor air, I cannot tell you if I'm generating a lot of particles or not. You have no idea about it. But if you could monitor just particles larger than 1 micron, what you see is that when students enter, they create a big spike. And when they sit down, the particle numbers go down. Carbon dioxide goes up, but particles go down. The particles are settling down slowly. They fall off. These are big particles that I walk in and they resuspend. And then the next students come, or when the students leave, they resuspend. When they come again, they resuspend. And then when they're sitting in class, it goes down. All right. But when they're sitting in class, people are breathing and they're putting out particles. So there is so just to remind you, when we are sitting in this class here, so firstly when I walk in, I'm going to put a big spike of particles, and then once I stop walking, it is going to decay. All right, and then when I start talking and breathing, I put a spike of particles, and that will keep building up as long as I continue to talk. So what I get is, so maybe when I first walk in, I get a big spike of particles that will level off. Now everybody has sat down, those particles will slowly decay out. But as I start talking and people start breathing and so on, we put another spike of particles, and the magnitudes are very different. The initial walking in is where we put a lot of particles, and then when I'm talking, I put fewer particles. So as this is coming down and this is going up, you don't see this climb until maybe the end of the class, where all the big particles are settled down, and then all the talking particles are now dominating. So if we sat in this room for 3 hours and I were talking continuously, you will see that as we walked in initially, there's a big spike, and that will come down. My talking aerosols will eventually pick up. But in 45 minutes, 1 hour, the initial resuspension is still the dominant visible particles. So here's what we did. We measured the concentrations of particles outdoor as a function of particle size. So we took this high cost instrument that can do size distribution. So it shows me in the outdoor air, you got particles all the way from 500 nanometers to 3 micron and beyond, but it goes down. So it's log scale. Most of the particles, big amount of particles are in the 500 nanometers to 700 nanometers. Beyond 1 micron, it starts dropping quite significantly. Then we know what we have for a filter. All of these particles are filtered and brought in. And when they're filtered and brought in, we know the filter efficiency, which depends on particle size. So for MERV 8, MERV 13, we know the filter efficiency. So we can calculate what should be in the room if there is no activity in the room. If there's no activity in the room, just, outdoor, you're filtering it. What would you have? You would have the blue particles, blue lines. But what do we actually find? We actually find red. What does it mean? So yes, so you can see it's reasonably matched here. But in here, there's a big difference. So all of these, the difference between blue and red is a human-generated particles. That's coming from us breathing and talking. So we did analysis of that to figure out how many of these particles are we putting in. So what we figured out from these sorts of analysis for carbon dioxide rate, how much are we emitting out? So we are in controlled studies. They said that CO2 emissions work out to be about 15 liters per hour or so, and what we are finding is it's closer to half that, about 6 liters per hour. That's what explains per hour per person. That's what explains the CO2 emission rate. How much are we emitting out? How much are we emitting for particles greater than 1 micron? These are the ones that are infectious, cause COVID, and so on. People have done very controlled studies where you put you have a standard floor. In a room, you make them talk or breathe or walk, and then depending upon what the activity is, and so on. Then they found that the values are about 1 million to maybe 10 million particles. What we found is it's somewhere in between. It's about this is more like 10 power 8 almost. So it's like 100 million, 1 million, 100 million. We found it's right in between. It's about 10 million particles per hour per person. That's what we're putting out, above 1 micron. Still a lot of particles, but but we have figured out that. So that's a number from actual measurements of real activity, as opposed to these controlled studies. With controlled studies, what you do is you often give people a book to read, or a phrase, a constant phrase to say. You pick people in a certain size range and so on. Here, somewhat random, right? And different voice, different volume. So we just let people talk naturally, and so these numbers are very realistic. But in terms of the experiments, are not too different. And then we figured out, from just analysis of the last 20 minutes of classroom data, we can figure out what is the rate at which breathing and talking particles are coming out. And what we found is that, yes, similar to experiments, the sizes are around 1 micron. But what we were able to observe is an emission rate of about 3.2 into 10 power 7 particles per person per hour is sort of what we believe is resulting from breathing and talking combined. And then we got some decay rates and so on. So now we can put in our models real values that we have from experiments in a real world setting, not just in a lab setting. And so before we do that, before we look at that some more, how we can use the data, it's still ongoing work. We don't have all of the modeling done. We finished some of the experiments. We've got these values. We got to put in models. Okay, so just I want to just get to energy implications real quick. And so what is it? So with our energy monitors, here's what we figured out. The amount of energy used by fans, when it's going full speed, when it's very cold. So this, by the way, is temperature. When it's very cold, when it's below about 10 degrees centigrade, fans are working non-stop to provide heating and cooling. As it gets as it gets slightly, in a more moderate temperatures, the fan energy seems to vary a little bit. You might be bringing in more outdoor air, less outdoor air. You may not need to move the air as much, because when it's very cold, the room is also losing heat. The walls, it's not just the people the people are putting some heat out, but the building is losing a lot of heat. So you need to make sure that you pump in heat more often. So air has to be pushed in all the time. But when the temperature is optimal, you don't need to do that. So the blue is, again, when the temperature is sort of optimal, the blue, which is the fan energy, decreases. But here's what's interesting: the heat pump energy, which is how much of heat you're putting in or taking out. The heat pump can either heat or cool, but heat that we're putting in or cooling is close to zero once you get to about 15 to 20 degrees. So when it's 15 or 20 degrees, we can just bring outdoor air. That'll provide the heating and the cooling required. We don't need to provide additional heating and cooling. Below that, we need to provide a lot of heating, and above that, and also this is still ongoing data. As it gets warmer, also you got to provide more cooling. But because a lot of our semester ends before it gets too hot, we don't get a lot of data in summer. This classroom is not occupied in summer. So trying to fill this data is a little bit more difficult for us right now. Okay, so in terms of air quality, so air quality versus comfort, how did we do? This is over a 6-month period. We monitored energy, we monitored all those particles there, and so we said, what is the air quality, what is the comfort? So here's what you can see. We called comfort index as if we are in a very good temperature range, 22 to 24 degrees centigrade, relative humidity is 40 to 60%. We call that comfort, we scale the comfort as 0 to 100. Above that, we made it as being uncomfortable. We started giving it bigger numbers. What we found is that, and this is the air quality index. If it's below 100, it's good. Above that, not so good. And the air quality index is if carbon dioxide is below 1,000, then the air quality index will be below 100. PM 2.5 is below 12 microgram per meter cube. That'll be below 100 and so on. So what you see is that air quality is almost always pretty good. So even the students are putting out a lot of carbon dioxide, bringing in outdoor air, the ventilation system is able to keep it mostly good, except for a few times. But thermal comfort is not very good. And it's not because of temperature, which is easy to maintain, it's relative humidity. When in winter, when we add heat to heat the air, we also make it very dry. So we're not really getting, we want to be in this box within 100 to 100. We're not always there. We are oftentimes very dry. So thermal comfort is very difficult to maintain. But particles and carbon dioxide, it seems like we have maintained all right. By the way, what we're finding is that we're putting a lot of heat pump to heat the air, which is keeping the temperature good, but the relative humidity creates a problem. We'd like to ideally put everything in that box. Okay, so here's what we did. Last fall, we ran an experiment where we said, okay, we saw this data, and what we found is that there's a lot of data. We understand some background. We didn't do any changes. We were just trying to monitor the system. Now we said, let's start making some changes. So we defined two operations, baseline and variable. So we let the facilities, the university ran that classroom by themselves 1 week. We ran the classroom temperature, all the air quality and everything else. We ran the system for 1 week. And then they ran for 1 week, we ran for 1 week. So we alternated it for about 4 to 5 months, for about 5 months. All right. And we were trying to understand whose system would be better for air quality and whose would be better for energy. So we call it baseline, which is a university-driven system, variable, which is driven by us. Our decisions are based on sensor data. When we see the carbon dioxide is high, we say bring more outdoor air. All right. If the particles are high, we say drive the air through the filter more times. And then when we say there's nobody in the room, let's slow the system down. We don't need to get to 400 ppm very quickly. We don't need to clean the room quickly, right? If we all leave for lunch at 12:30 and nobody's going to come immediately, we say go slowly. And when suddenly somebody comes, we quickly speed up. So now we want to know. So ours is what our variable one is all sensor driven. Theirs is based on how they think is the best to run. So here's what happened. So at the end of the 4-month project, we looked at carbon dioxide. During the baseline, this is when it's unoccupied, which is usually Sunday, and in the evenings. When it's unoccupied, we assumed it's unoccupied. They actually had very low CO2, very low. We had more variable CO2. But that is because we just let the system loose. We said, don't bring so much outdoor air when nobody's out there, right? So if it's very warm outside, very cold outside, bringing it and cooling it and heating it is just waste of energy. We don't need to do that. So our system was able to tell them, so which resulted in higher CO2, but there's nobody in there, so it's no big deal. But when it was occupied, you can see that we actually had slightly lower CO2, and we didn't have any big spikes. We had much lower spikes. So with our system, we had better CO2. For particles, it didn't change much. Our system is not very, we live in a rural New York village where there is no, air quality is not a big problem. So unfortunately, we didn't have anything here. But energy, look at this. So we reduced CO2, right? So which means we improved air quality. And here's the energy for baseline. This is what the university is running. Okay, for baseline. So you got to the color. The x-axis is temperature. So it's very cold here. It's getting warm here. And the color is a fraction of outdoor air. You're bringing more outdoor air means it's yellow. If you're just recirculating the indoor air, it's blue. Ideally, you want to bring more outdoor air. That makes it safe. If you're just recirculating indoor air, we are probably breathing each other's particles. So what do we see? When it's very cold, they don't bring too much outdoor air, which makes sense because it's very cold. The system cannot heat up. When it's minus 10 degrees, it cannot heat up a lot of outdoor air. So they bring only about 10%. When it gets very warm, also they want to bring less outdoor air because they don't want to cool down that. In between, they bring more outdoor air, all the way up to 100%. And then this is VFD, variable frequency drive, if you guys know. That is basically, when the fan, it can speed the fan up or slow the fan. So we added that, and instead of running always at 100%, we can slow it down. We can slow it down to 50, 60%. So you bring less air if needed. All right. They almost never used it. But with our algorithm and telling them to use it, so here's our variable operation. Firstly, our energy is all over the place. Compared to them, we are all over the place. Because in our system, we're asking them to change it all the time. All right, we're asking them to change all the time. So what we are able to do is, again, when it's 10 to 15 degrees, we are actually able to use very little energy by bringing a lot of outdoor air. Very natural. So what they were doing is they weren't bringing as much. They were not bringing it as much outdoor air. We were able to bring a lot more. But sometimes we were asking them to bring less also outdoor air, depending upon occupancy and so on. All of this meant that it's a much more dynamic system. We're changing things a lot more. That's shown by the colors, shown by the extent of operation here. The extreme cold, extreme heat, we didn't change, but everywhere else we could change. What is the benefit? When it's unoccupied, here is the median usage of energy versus with our system. This is when the university was driving in, the median usage was about 25 kilowatt. With ours, was about 10 kilowatt. All right, it's about unoccupied. There's some again, if you look at the whole statistics, not just the median, there's about 33% savings in energy. When it is occupied, again, we have, depending upon usage, depending upon the weather outside, we can drop quite a bit or not. But again, there's the energy estimated savings was about 42%. And the energy measurements were audited not by us but by a third party. We weren't trying to regularly watch the energy and change it. We made our changes without looking at the energy at the end of only at the end of 5 months we looked at the energy. So we were able to both reduce carbon dioxide, right? We were able to reduce carbon dioxide a little bit, and even particles were, again, this is the safe limit is at 12. We're nowhere near that. So we did not compromise on air quality. We actually improved it, if anything, while saving energy. All right. So this whole paradigm was that if you try to improve air quality, bring more outdoor air or reduce particles, it would mean more energy usage. It's not true. We broke the paradigm there by saying that with sensor-driven systems, there are times when you are going to spend more energy to keep good air quality. Agreed. But there are opportunities for saving energy that if we can take advantage of that, the net result is you will save more energy and have better air quality. At any one instant, you might be one way or the other. All right. So where are we going? We want to minimize infection spread. So we understand now what's happening with particles and so on. So we want to minimize infection spread. And particles, just by reducing PM 2.5, it doesn't mean I've minimized infection spread. I need to be able to detect biological particles. And we need to minimize that. So maybe my air quality has gone down because outside air got cleaned up, maybe magically, right? Maybe the difference between one room or the other might be where you're taking in the air or something, but it may not mean that I've reduced the biological intake. So can we select particles? Can we find particles that are just biologically active? So that's something I'll talk about in the talk in the afternoon in chemical engineering department. And then, the ventilation system, we did sensor-driven system. It's still not a real time. It's still based upon rules, but sensor-driven rules. Can we get even smarter just to have the sensors drive it? That's sort of where we're headed. Just real quick, I know we're probably running out of time. I'll talk about something I've not talked about before is what is the uniformity there? The models that I talked about before could only predict an average concentration changes in the room, but in reality, pockets in the extremes might be different. And also, for infection spread, if I'm sitting here and you're sitting across the table, or somebody sitting far away, what are the risk factors? So all of that require more detailed analysis. Just as an example, here's some measurements. 4 different spots in the room have very different concentration levels. So variability is important. Okay. So here's our modeling. We modeled the room fully in computational fluids. I don't know if this will work. Okay, so so we can inject variable amounts of flow. We can see what is the fate of carbon dioxide. With time, we can look at fate of particles with time. So all of these requires turbulence modeling, unsteady flow modeling. We've had to figure out a way to tie in the airflow going in with the airflow going out, because some of the pollutants are recycled back. So all of that is accounted for, and the work is still ongoing. And I want to say that we have not exactly still captured all of the information. So for example, here are experiments. These are very different scales, but here's the theory line, and in the front, left, right, and back of the room, we got different colors. And here's the CFD modeling. All we can say is we don't match. All right, this is still work in progress. We need to keep working on the resolutions. Already the simulations take a long time. These are very slow simulation, size of the room, the mesh density, and so on. I was hoping we'd have some experimental validation. All I can say is that we can capture variability, but what we can't capture is exactly what's seen here. And part of that is because the CO2 here is driven by kids not sitting uniformly in class. We don't know where they're sitting in the class. Right? If you sit more in the front or more in the back, it can affect. So we need to run more experiments for our validation that are where we inject CO2 in the room rather than just rely upon real data. And once we validate that, we can put students in different rooms. So the validation still, we believe the modeling is okay. The experiments need to match the conditions of modeling, and that requires new experiments. Our new sensor that we can start detecting kinds of particles, not just telling you how many particles there are, and then drive the ventilation system. If I'm in a hospital, I would want to drive the ventilation system to just minimize biological particles. Those are the number one threat, right? So that's something how we will do that. I'll talk about it at 3:30. And that sensor is now in the space station, the International Space Station, making measurements as we speak. I'll show you a little bit of data that's coming down to us. Those sensors are we have built it so it's almost insensitive to composition. There's ammonium sulfate, dust, smoke generated from Velcro, or several orders of magnitude have very minimal dependence on composition. I'll show you more data where there's very little dependence on particle size and so on too. More interestingly, I'll show you some very initial work that allows us to classify dust. As to what is a particle ammonium sulfate, it's a particle dust. Machine learning of signals, we can find that out. All right, I know we're out of time, but I'm going to just summarize real quick here. So again, this ventilation optimization is what we might call a multi-objective, multiple competing goals. Multiple objective because we're trying to get temperature in this narrow range. We're trying to get relative humidity in this narrow range. We're trying to get pollution, CO2 level below a value, PM 2.5 below a value, VOC below a value, and so a lot of objectives. And then we have got a somewhat competing goal here. While we try and keep all that low, we want to keep our energy also low. We can't take a brute force approach. A brute force approach would be just putting a HEPA filters all over, right? We would get our particle population concentration down to 0 with HEPA filters running at thousands of CFM. But then energy is a problem. So how do we get that? I think these air quality sensors allow for it. Because as we've shown with the sensor-driven ventilation system, we could reduce CO2 and energy use, right? 30 to 40%. That's amazing reduction in energy. And when you think about the US ventilation systems use a lot of energy. I give you a number of about 10%. And if you can really save 30% for space, that's pretty significant. But for particles, sensors are not good enough. They don't give you size-based measurements, so it can't distinguish, some of the human-generated particles from outdoor. They don't do composition, and all of those are problems. And then the next step is, so right now we are combining sensors with rules-based. Saying, if my carbon dioxide level is this, do this. But as just as a very simple example, I might say the carbon dioxide levels are high. Open your windows, for example, right? But I need to know whether your windows are openable or not. And that knowledge, because every space is different, right? If you take just an IIT campus, you probably have 10,000 rooms, let's say. You can't put a different rule for every single space. And what if that changes? What if you change the window from being openable to you seal it somehow? Then the rule has to change, and the facilities cannot keep up with that. So that's where AI comes in, where we can figure out over time, which rules work and not, and the rules have to be constantly updated. And eventually, it has to be smart enough to say, this room can only do these things, and based on that, what is the best approach to optimize air quality? And that's something that we're just about beginning to do that. The CFD simulations are important for us to try and understand just, how do we redesign these spaces? Some of it's going to be in the end, here's the limit of what we can do. And how do we redefine the space and ensure thermal comfort and air quality is more uniform across the space? Infection spread is minimized. Let's say here occupancy is mostly here. There may be appropriate locations of outlet vents and inlet vents. From a thermal comfort perspective, it may be really good to put cold air on me right now. But from an infection spread perspective, it may not. It may be the opposite. It might be pushing all my particles to you guys. So if you all fall sick tomorrow, you know where the source is, right? So that's something that I think there's probably scope for redesign. So anyway, so we are looking to start some work on integrating biosensors with ventilation system in Clarkson starting next month or next semester. And then the optimization, while we showed this optimization of one of the rooms, we're looking to expand it some more and also add more controls that the algorithms are getting deeper in there. And then trying to again combine all of this data into a digital twin so we understand again from a redesign perspective this will become important. So that's all I have. I just want to have a quick acknowledgement, funding and the facilities. So a lot of the I don't know how it is here for us to make any changes to the building operations, it's a lot of work. It took me about 5 years of work to work with them to convince them it's okay for us to change it. Because they're very, very afraid we're going to break it. And if we break it, they lose their job. I'm a tenured faculty member, they're not. But they're very kind. They've worked with us for about 5 years, and now they allow us to go in there. They use our recommendations to change it, and based on what they've learned, they're changing other classrooms even without our energy sensors to try and change their operations based on what they've learned here because of the energy savings that they're seeing. And then a lot of the initial work was done by Chaitany's PhD now in Brookhaven National Lab. We have a couple of students who are working on this now, and some of the sensor work is done by Srikesh, who was a PhD student from, I forgot his advisor here, but I'll try and remember after the meeting. But yeah, he's finished PhD from MIT and he's been working for us about a year and a half. So thank you for your attention. I'm going to answer questions.
Yeah, thank you, Suresh. It's a wonderful talk and very insight in terms of sensors being used in various energy and ventilation control in the indoor environment. Maybe the first, I thought some discussions to look at it. How many sensors may be required in order to design? Because, for example, this can be in one large hall, and there are 4 air conditioners that are required. We all sit in different places. I will look into that. How many sensors that need to be kept in order to make sure that.
Yeah. No, I think this is a really good question. There is no one answer, unfortunately. As an example, if we had one person in this room and they're just running around, they're going to stir things up and it's going to be uniform. All the concentrations will end up being uniform. But if just there's 2 of us sitting here and talking, it's going to be very non-uniform there, right? So it's very much activity driven. And so if it's just the 2 of us here and one person is sitting there, the single sensor sitting in the space here may not tell us what emissions somebody there might be getting. So it all depends on the questions we are trying to ask, and that's why the CFD becomes very interesting. And what the CFD can tell us is what are the error bars in our estimation. And so my recommendation, if I have to recommend, right, is that we in the optimization we should also put in how do we minimize the number of sensors. Like they're expensive, and do we really need 4 or 5 sensors here? I suspect we can get away with 1 sensor in the outlet vent. If you have an outlet vent, like in your office, there's in and out, I believe, and in the outlines, if you put in, it represents an average in the room. So it's sucking out from the room, it's coming from that corner here, and so on. In the classroom there, we had 2 outlet vents, and they're very different numbers. So we put 2 different ones, and again, those numbers change whether there are more students sitting in the back or front. So we've seen that about a sensor in a well mixed space, even if it's about 4,000 square feet, you can get away with 1 sensor. If it's not well mixed, about at least 1 every couple thousand square feet is a good idea. If cost is a concern, 1 in the outlet vent, per outlet vent. If you have more outlet vents, not a bad idea to put more. If it's a small, like an office, like our faculty offices, you could get away with 1 sensor in the room or in the vent. In a bigger space like this, 1 in the vent, or it may be more depending upon activity.
So just to follow up on that, if it's the energy sensor, there will be a cost involvement.
Correct.
Can we, suggest that if you bring out this kind of an, management system,
right,
it reduces the energy cost, so that there will be a lot of saving over a period of time. Did you do some cost estimation on that?
So again, the building management systems are necessary in complicated environments, especially like in a hospital where you're keeping both temperature in a very, very tight range, humidity in a tight range, and you've got some rooms that are under pressure, some over pressure, and so on. That sort of stuff to keep, you need these building management systems. And if you take that experiment that we ran, where very experienced facilities managers were setting the temperature conditions, and was this our system that was, you know, on its own trying to set we were able to save by 30%. So I strongly suspect that sensor-driven operation, and by the way, these numbers, while they're shocking to us, because we're expecting 5% reduction or so, they're not completely unexpected, because the Department of Energy in the US suggested that sensor-driven systems can save 30% energy. So these numbers, now going back and looking at it, are not completely inconsistent with some of the expectations. So I do think that even after you put in the capital cost for driving this, by the way, in that system we put in a VFD, variable frequency drive, in the classroom that didn't exist before a project, and that was about a $2,500 investment without labor. And I think we will get that back in 5 years in that room. And the return on investment is about 5 years in that room. So upgrading, depending on usage and so on, if you have because we have a very dynamic usage, that VFD feed off. If there's 20 people in the room all the time, you're not probably going to be varying the flow as much and so on. So depending on the room, I think many spaces. That's the next thing actually we're just doing right now, is we are now evaluating what is the potential savings. So what we're doing is we're just saying, what is the energy you're putting in? What are the outdoor conditions? What are the indoor conditions? And how could you have run this better? And how much would you have saved? So within about 6 months, maybe in the US, because there's a lot of temperature changes and so on, if you give 4 to 6 months, we could easily very exactly estimate how much energy could you have saved by putting in what block in there. Putting in a VFD, putting in filters and so on. What air quality improvements can you get? What energy savings can you get?
Thank you. So just please see some other questions from any of you.
So the theory you have modeled, like the box model is like one complete for the entire room. Why not like divide it into smaller voxels and cubes and then?
Yeah, no. There's a lot of list recommendations for a building. Now, usually you don't do it for room, but you'll do it for buildings. So you have a room and another room, and you have intersection between them and so on. But simplest is the easiest to use. And the problem is, if you take a room, our inlet is spread out fully, and there's a constant exchange. It's a very complex exchange. The CFD videos showed very complex flows. So it's very difficult to divide that space up, in any meaningful manner. So there's no real way to break it up. So, but if there was, yes, you could probably improve upon it that way. But the gains would be very minimal and it would be very complicated.
I was just thinking, we take like one student sitting, we just make that as a cube, and then we do like every space like cubes, and then if the student is occupying, we just switch on that voxel, and then we can switch off the places which are empty. So I was just having an idea.
The non-uniform distribution of sources can be done better than what we have. So in here, we have an emissions emitting everywhere uniformly, so like students are sitting in every centimeter square. The theory breaks down a little bit once you start doing that. It gets pretty complicated. It's not a simple ODE with a simple equation. It can be done, maybe, but the simplicity is gone. Yeah.
Rate of particle from the breathing and talking.
Right.
So, how do you calculate it? Because in the room, both students and professors are there, so maybe not all students are talking. So
we're hoping no students are talking until except for question. But there are assumptions being made here. So so what we have done, I don't think I can draw here, but the bottom line is, we can this drawing here. Let's see. Okay, the way it draws. Okay, so as soon as students walk in, there's a spike. And then these particles all settle out. So it turns out a lot of these resuspended particles are usually larger particles. But they actually overlap. The mode size is probably a little over a micron or so. And then, if I'm getting really fancy, I would use a different color. Okay. And then as the students start breathing and so on, their intake goes up and up and up and up. So it's only if you have a long class, about 20 students, can you really capture that. So what we do is we take the initial data, we figure out the decay for that. Then we take the, because we assume that the initial aerosols are very small, and then we just let that, we model the decay, and then extract what other source, with what characteristics would explain the observation. The observations usually decay nicely with an e power minus t alpha t, but then it stops decaying nicely. And that is because there is the source starts picking up. So we can figure out what source is needed to explain that. That's sort of how we arrive at those numbers. But there's a lot of approximations there. And it's because we don't control the class, we live with the data we get. Thanks. Good question.
Thank you very much. I think it's very good. So thank you all for joining this this air quality management lecture series talk, and thank you very much on behalf of department and Air Quality Management Association and AQML conference. Would like to thank Suresh for sharing his time.
Thank you for the invitation. Yeah.